Okay, as promised, I'm going to continue with our next modules 6. In this module, we're going to cover our cascade counter. So this is the new subtopic, but still under module 8. So over here, let's say we do some recap, which is what we already learned previously. I think you can easily read it because we just learned it yesterday. Okay, take your time and read it. And now let's move to our cascade counter. Counter can be connected to achieve higher modulus operations. Cascade means that the last stage output of one counter drives input to the next counter. So what is the meaning? Here is the example. If let's see you have two counters, which is modulus 4 and modulus 8 connected in cascade. It can achieve count until 32 clock. Why? It's because 4 times 8, then you will get modulus 32. So from here you can see you have modulus 4 counter, which is 4 counter, and also modulus 8 at counter. How you're going to see it? To the power of 2 you get 4, to the power of 3 you get 8. So that's why you have 2 JK flip-flop at modulus 4 counter, and also modulus 8 JK flip-flop you have 3 flip-flop JK. So if let's see module 100 counter use 2 cascade decade counter. How? Decade is 10, of course. So 10 you have 2 means that you have 2 10 or decade counter, you get a total of modulus 100 counter. This counter can be viewed as a frequency divider. So it divides the input clock frequency by 100. So this is the example on the clock frequency. And 3 cascade decade, you can see 10 10 10. You can perform the divide by counter perform a divide by 1000 frequency divider. So basic clock, you can read this. Total MOD or modulus is 10 the power times 10 times 10, so you get 100. So MOD is the short form for modulus. So here there is example, which is 2 type counter modulus 4 and modulus 8 need to be used to achieve counter up to modulus n and then n clock. How cascade counter can achieve counter until 32 clocks? So this one you already looked into previously. So what is the frequency produced by each counter given in initial frequency as 800 megabytes? So you need to check back on the frequency. What is the equation for you to get the frequency? So if let's say you were given the frequency at the clock given, let's say over here initial on your frequency clock is 800 megabyte. So you can see over here the example, this is the Fn is the initial value of your frequency. Then after that you're going to get frequency divide to 10, and then after that frequency divide to 100 after 2 times of 2 decade counter. That's why let's say you have the initial value of your frequency is 100. So after that until up here what is going to happen is 100 divide to 10. So you get the frequency here is 10, isn't it? So over here at the end or similar to the equation over here, what is the frequency produced, which is this is the output or the end or the produced output. So over here you will get 100 divided to 100, then you get the produced frequency. So you can see over here this counter can view as a frequency divider. This is what the meaning by that, and it's divide input clock frequency by 100. But if let's say you have over here the difference is you have 4 and 8, so you need to draw I just draw a block, okay, as you know that I'm going to draw ugly. So over here your modulus 4, so your modulus 4 you need to know it's going to divide to 4. So let's say you have 800, then you divide with 4, what is the frequency, and you are putting this frequency to the next modulus 8. So that's why your answer here what you're going to get, I think 200, is it? So correct me if I wrong, I didn't calculate it. And you should divide it into 8, then you will get the frequency produced. Please check also in your module, it's not stated over here, so try the examples that in your module also. So here you can see there is a 4-bit synchronized binary counter. This is how it's look like. There is a dedicated counter which is with this IC, which is a mode 16 counter IC. The starting counter sequence can be changed by setting the initial value, so you can try to read it, and to load must be 0. So you need to see over here why you need to be 0, because it's bar. So this is just examples on 4 bits IC74HC163. So cascade counter with cascade sequence. The cascade counter below has 16 to the power of 4 states, full modulus for 4 cascade. So you can see you have 4, 1, 2, 3, 4. And if we need a modulus for 40,000 counter only, so how you going to get only this, because overall altogether is 65,536. How you going to get only this? So you need to determine the initial value. So this is the initial value. You need to minus 40,000 so that you can get the leftover. I just said it's leftover. And make the counter start at this count. So you need to start from here. Then after that, if you counter until 400,000, you get until the end of 65,536. You go it all together 40,000 counter. Therefore, preset the cascade counter called as 66016 by setting the value D3 over here. Where is it over here, as shown and as below. So you need to set up first the initial value, the present cascade counter, or the current one. So this is on the cascade counter. If you didn't understand, as usual, please WhatsApp me or ask me in the class. Okay, now we move to other subtopic, which is under analysis of sequential circuit. So you can see over here, this is analysis sequential circuit, the behavior of the sequential circuit. So it determined from input, output, and the states of each flip-flop. Both of the output and the next states are functions of the inputs and also present state. So you can see the logic schematic move to all the sequence that you need to know on when you want to analysis of the sequential circuit. First, you need to derive the execution equation, and then derive next state and output equation, generate the next state output table, generate next diagram, and develop timing diagram. So this is follow all the steps, and you need to know what is on the detail for every step, all together 4 steps. So if let's say over here we're given the example, so you need to follow all the steps also. You need to have 4 steps. So the example, derive the state table and state diagram for the sequential circuit below. So you need to use the method 1. This is the method 1 under modulo 4 counter. So first step, you need to come out with the Boolean expression for the input of each flip-flop. So you need to see each flip-flop. This is the flip-flop 1. This is the flip-flop 2. What is the equation for both? So you can see over here. This is how basically the Boolean expression. You can see the input over here. It's connected to Q, and then another one is like this, which is from your CNT, and this one is your clock. So when you're going to get CNT, no, is it? No, yes. And sorry, it is Q0, because this is the flip-flop 0. And then you can see how you're going to derive it. From this, you're going to derive it. Sorry, the one is correct. This one you're going to make it as a standard form. So this is also, you need to have the Boolean expression for each flip-flop. Then second step, derive the next stage equation by converting this execution equation into flip-flop characteristic equation. In the case of the flip-flop, so you can see over here, you need to derive the next state equation. So you need to come out with the next. This is the one that you also can refer. So step 3, you need to construct the next state table. This one also you already looked into our previous class yesterday. You just apply it with another different schematic diagram. And lastly, the step number 4, the state diagram is generated directly from your step 3, which is next step table, state table. Then after that, you can come out from this table to the state diagram. This one also I already show you how you're going to get. So please try it and remember back. If you cannot remember, please go back to previous video, yesterday video, and try to do the state diagram from the basic thing. So this one is just an example. Okay, now is under method 2. You have another method for you under analyze of sequential circuit. So method 2 is using JK circuit analysis, which is if you were given the sequential circuit with 2 JK flip-flop, there is one input X and one output Z. So you're going to use this method too. So you need to follow also the case. Sometimes you were given only the case, but you need to pick which method are applied for it. And you can follow the step as usual. So over here, draw the state diagram. I think this one is similar also. You can try also this exercise. Actually it already given you also the answer. I think there is also several exercise under your module. So this is another exercise, and basically analysis is only on more to exercise on your understanding what you already learned in previous subtopic. So please try to do it all the example. So I think only that for our module 8. So after this I will come out with a new video under our module 9. Then we finish our all module from module 1 until module 9. So let's move and focus to our module 9 later on. Thank you and have a good day. Bye bye.